9.7, integrals of vector functions and projectile motion. It's a continuation of 9.6. Students will integrate vector functions and solve. So how is integration used to find a position vector? Well, if we're given something like velocity, we can integrate and get to our position vector, just like we did with function notation. So let r equals r of t be a vector function whose domain is the closed interval between a and b. The indefinite integral of the vector function r equals r of t is found by integrating each component of the vector function separately. That is, we will integrate the x component and also integrate the y component. When finding the indefinite integral of a vector function, we insert a constant vector of integration after integrating each component. That's a lot of words for plus c, right? When we integrate, we need a plus c. So example 1, let's find the integral of e to the t ln of t. So we're going to integrate each piece separately. So we would integrate e to the t dt. That's your x component. And then for your y component, we'll integrate natural log of t dt. So these are two separate things. You're not going to do any product rule, no integration by parts or anything like that. You'll find the antiderivative of each one separately. So the antiderivative of e to the t is e to the t plus c. And I'll mark that with the c1. Now, the antiderivative of natural log, this one's going way back. The antiderivative of natural log is not on the golden ticket. That's not the answer to any derivative problem. So the way that we found that was through, remember this guy, LIATE? And we have a logarithmic, and you actually have an exponential, and you had to do uv minus the integral of v du. Yeah, take a second and try that one out, but I'm going to save us some time. This will become the natural log of t minus t plus another constant of integration. All right, just had to make sure I had my signs correct. Now, we don't want to leave the constants of integration on the x component and the y component. What we can do is combine those together for another plus c at the end. So I know this looks a little strange, but this will be e to the t natural log of t minus t. And then I can just make one super huge plus c on the end. And there's our solution. So it is that straightforward. So in example 2, I see boundaries. So what do you suppose we're going to do with the boundaries? We're going to substitute those in for the fundamental theorem of calculus. So example 2, find. So let's look at example 2. We want to find each vector integral. So to find each vector integral, we need some antiderivatives. So if I rewrite the vector function with the integral inside, it will look a little bit like this. So if I find the antiderivative of the first piece, I have 6t cubed over 3 minus t squared over 2. This is evaluated between 1 and 2. Then I have 4t squared over 2 plus natural log of t, also between 1 and 2. So what do we have? We've got 8 times 2, this is 16, minus 4 over 2, which is 2. And then I have 2 times 4, this is 8, plus natural log of 2, minus 2, plus natural log of 1. All right, so in the beginning, 16 minus 2 gives me 14 for the x component. For that y component, 8 minus 2 is a 6, plus natural log of 2, and I know that the natural log of 1 becomes 0. So 25 over 2 is 1.5. Apparently, I'm in a little bit of a rush this morning. I forgot part of the x component. We're going to have minus forgot to put the 1 in as well. So if I put in a 1, here's a 2, and then minus 1/2. Let's see, so we have 14 minus 2, which would be 12. And then minus negative is really plus, so 12 plus 1/2, so it's 12.5 or 25/2. And that second piece is 6 plus natural log of 2. That's still correct. All right, let's see how we do on letter B here. Letter B, I want to integrate e of t and e to the 3t. So no boundaries on this one, fewer places to make mistakes, which is good. So we have the integral of e to the t dt and the integral of e to the 3t dt. So the first piece, the antiderivative of e to the t is e to the t plus the c. And then the antiderivative of e to the 3t is going to be e to the 3t. There's really a u substitution here, which comes from the chain rule. So instead of multiplying by 3, we divide by 3. You could go through the process of u and du and rewriting it. That would work. Here's another constant of integration. But recall that we put those constants together at the end. Okay, there we go. That's letter B. Example 3, solve the vector differential equation with the initial condition r equals 0 of 1, -1. So if you recall, when we have initial conditions, those allow us to solve for c. So I have the differential equation means I'm given the derivative. So if I want to go to the initial function that's not the derivative, I want to go to the original, we're going to integrate it. So we are going to integrate 2t dt, and we're also going to integrate e to the t dt. So I guess the way I could write this is r of t is equal to the integral of r prime of t. So the antiderivative of 2t is going to be 2t squared over 2 plus my original c. And the antiderivative of e to the t is e to the t plus a second integration constant of integration. There we go. Now, r of 0 equals 1. So in my x component, I know that the t value is 0. So this would be 1 times 0 squared plus c1. Well, this has to be equal to 1. So 1 times 0 squared is 0. So that first constant of integration is 1. When I work on the y component of this vector, the antiderivative of e to the t we said was e to the t. So if I put 0 in place of t, I have e to the 0 plus that second constant of integration is equal to -1. So 1 plus c2 equals -1. c2 is going to be equal to -2. So when I put these together, I just rewrite my vector function, but with the c values. So I have t squared plus 1 e to the t minus 2. And that's our final answer. I'm solving that initial condition. Example 4, an object travels in the xy plane along the curve traced out by the vector function r equals 1 minus t to the 2/3 raised to the 3/2, comma t, in meters for t greater than or equal to 0. Find the total distance traveled by the object from t equals 0 to t equals 1 second. So what happens here is we have something traveling along. Whatever it was went all over the place. So my object that's traveling along this curve, I don't want to know the displacement. I don't want to know how far it is from the beginning to the end. I want to know how far did it travel. So believe it or not, this is your arc length. So we're going to set up an integral. The integral in this case will go from 0 to 1. And inside, if you recall, is that speed formula. All right. So when we integrate speed between 0 and 1, we will get the distance traveled by this object from t equals 0, went around this path over here to t equals 1. So inside the speed formula, if you recall, is going to be the square root of the x component squared, the derivative of the x component, plus the derivative of the y component squared. All right, the x component's a little bit messy. We're going to have a chain rule in there, but that's okay. 3/2, 1 minus t to the 2/3. So the 1/2 times the derivative of the inside would be negative 2/3 t to the 1/3. I want to make sure I have all those pieces. This whole thing squared. Plus the derivative of the second term, luckily that's pretty easy, which is a 1 quantity squared. This is all still inside of the radical. So uh, 3/2 and 2/3, those are going to cancel conveniently. So this is a -1. 1 minus t to the 2/3 raised to the 1/2. And this is a t to the 1/3. Plus 1. This first piece is still squared inside the radical. Okay, so -1 squared is 1. 1 minus t to the 2/3 raised to the 1/2 squared. Well, this is just 1 minus t to the 2/3. And that t to the 1/3 on the end, if I square that, I can multiply those exponents. So this is t to the 2/3 plus 1. All right, let me just check on my work so far. All right, so I'm checking in my work. Did I mention it's a Monday morning? When I went to find the derivative up here, I brought 2/3 to the front, which was good, and I subtracted 1, but this should have been a -1/3. And a -1/3. So that makes this a -2/3. So what the textbook did is basically distributed this through. So this is t to the -2/3. And then if I multiply t to the 2/3 times t to the -2/3, you add those two things, the two exponents together, and you get a 0. So t to the 0 is just 1 plus 1. The 1's cancel out. I have t to the -2/3 inside of that radical. So when we integrate this, believe it or not, we made it easier. It doesn't feel that way. This goes from 0 to 1. T to the -2/3 raised to the 1/2 power dt. So those exponents I can multiply together. This is really a t to the -1/3 between 0 and 1 dt. The antiderivative of that would be t to the 2/3 multiplied by 3/2 in the front. We put in the 1, we put in the 0, and the final answer would be 3/2. So when it talks about total distance traveled and you're in polar or even, well, if you're in vector, parametric, or polar, it's really just arc length. It's really just arc length. All right, let me reset my screen. We've got one more to do, and then that's it. All right, we got example 4 shrunken out of the way. So example 5, find the velocity vector and the position vector of a particle if its acceleration is given by 0, -9.8 meters per second squared. We have our initial velocity vector, and then we also have our initial position between 0 and 2. So we've already done this with function notation. We'll do it with vectors. It just means we have to do it twice. So we have the x component and also the y component. So if you're given acceleration, if you integrate acceleration, you're left with velocity. And if you integrate velocity, you're left with position. So that's what we will do here. So our velocity vector, v of t, is going to be the integral of the acceleration vector. So we'll integrate 0. And we will also integrate -9.8. So 0 gets a constant, which would just be t, but that's going to remain 0. But plus that constant of integration, c1, negative 9.8, the antiderivative is going to be negative 9.8t, plus a second constant of integration. Now, this is where we use b sub 0. They gave us that information already. So 0 goes in place of the t, and those are the two things that we're equal to. So if we do the x component, we're going to have 0 plus c1 is equal to 0. So that means c1 is equal to 0. That's convenient. And over here, for the y component, we know that negative 9.8 times 0 plus c2 is going to be equal to 9.8. So c2 is equal to 9.8. So my velocity vector is going to be 0, negative 9.8t plus 9.8. Now, how do I go from velocity to position? You are going to integrate one more time. So my position vector, this time we have bar, is going to be the integral of 0 dt. And then the integral of negative 9.8t plus 9.8 dt. So the antiderivative of 0 is still 0. You put a t with it, it would still be 0, but we can add an integration constant. I'm going to restart C1 over here. It's a different C1 than the first step. I should probably use C3, but I'm not going to. The next antiderivative is negative 9.8 t squared over 2 plus 9.8 t plus C2. We're going to use 0, 0, that initial condition, to solve for our C's. So the x component is going to be 0 equals 0 plus C1. And your y component is going to be 0 plus 0 plus C2 equals 0. So C2 is also equal to 0. So when I put all of this together, R of t is going to be 0. Negative 9.8 divided by 2 is negative 4.9 t squared plus 9.8 t, and that c is equal to 0. Let me double check. And we got it. That was it. So I like Unit 9. It kind of brings everything full circle, back to limits, back to continuity, back to the equation of a tangent line, position, velocity, acceleration. So it all comes back together. Please let me know what questions you have. That's it. That's all of our new material. So from here on out, we'll review until we have an AP exam.